morning, good afternoon, wherever you may be in your day. Thank you, as always, for choosing to make chemistry part of your day. I thought as we near the end of the calculations for the thermodynamics chapter, it might be a good time to review what we should be able to do at this point, how we recognize these things, or, what tools we have in our tool belt. I like to think of myself as Batman, personally. Hey, I'm Batman. See? Very good impression. All right, so the calculation we're going to do, as promised in the previous video, is use enthalpy of formations or standard heats of formation to either get the overall heat of formation for a reaction or an individual heat of formation that's missing from a thermochemical equation. And it's very easy to recognize these. I'm going to do the harder of the two examples for you so you can see what that looks like. But before we do that, let's do a quick review. All right, we see a change of temperature in a word problem. That's going to be the Q type of thing. And oh my goodness, there's so many versions of that. It's so exciting. Who knows where it'll go? We could have a pure substance. We could have two substances, like copper, bar, and water. We could have a chemical reaction. This could be a phase change, like heat of fusion or heat of vaporization. Or it could be a chemical reaction, a combustion reaction within a bomb calorimeter. And we can mix and match those all up. So you got to be able to operate through those pieces. And whether you view phase changes as a separate type of calculation or not is totally up to you. We also did stoichiometry, which is kilojoules to grams, grams to kilojoules. We have to have a reaction with a delta H attached to it. So although a little bit not super obvious, like two temperatures to recognize, still, hopefully you can recognize that. And that is a maximum of a two-step calculation. So again, if you recognize this, I think it's the easiest in the bunch. If you're given two reactions, they want you to compare the reaction without the delta H to the one with the delta H, and that's all you have to do. If you flip it, you change the sign. If you change the stoichiometry, multiply by that number. If you have three or more reactions, what they want you to do is take the whole series of reactions and rearrange them to add up to the goal. And we did that reaction. So again, easy to recognize. It's easy to see two reactions. Easy to see three or four or five reactions. And now we're going to do ones where the magic word is of formation. It could be heat of formation, could be enthalpy of formation. Should really have the word standard in there. If you see of formation, that's a giveaway as well. And these are all done exactly the same. These are extremely formulaic. Heck, you could turn this off right now and Google enthalpy of formation calculations on YouTube, and I'm sure the top 30 hits will all give you the exact same methodology. But you will not get the bow tie. You might not see a board hit me in the head. You never know what'll happen. Who knows? Let's see what's up next. Concepts. I bet you already knew that. You've probably gotten the rhythm to how I like to teach. I like to talk about the concepts, what's going on, and then we apply it. It's not just a magic mathematical procedure without any rationale behind it. So, I always argue every year whether I should show this rationalization and how deep to go into it, so I'm going to do a surface dive into the derivation here, if you will. So, if we take a simple reaction, 2A plus B goes to 3C. We could blow those two molecules of A up into their elements. We could blow the molecule of B up into its elements. We could form C, or three molecules of C, from its elements. And if I were to add these reactions together, since it's a balanced chemical equation, however many, whatever elements are over here have to be the same elements that are over here, and they would all cancel out. And we'd be left with our overall reaction. So if we added up those pieces, it would equal the total. The elements would go away since it's a balanced equation. And if we really look at what we've done, is we've gone molecule to elements. That's the opposite of a heat of formation. We have two of them, so we've got to put a 2 out front. So using all those skills we just talked about in the last two videos, minus 2 heats of formation of A. Same thing with B. B to elements, well, that's the opposite of a heat of formation, so it's -1 heat of formation of B. And then C, elements to C, well, that's heat of formation. Remember, heat of formation defined as 1 mole of. We have 3, so multiply by 3. And now if we look at what we've done, you start to see where the stoichiometry comes through, and you start to see that all the products are positive and all the reactants are negative. This is the most common version of Hess's law. Hess's law is truly, if you combine two or more reactions, the overall enthalpy change equals the sum of the pieces. But this is kind of the one of the most pragmatic uses of Hess's law, and you see this one quite a bit. These symbols are intimidating, so I'm really thinking about just skipping this and showing you what they mean in an embedded problem. Calculate the standard enthalpy of formation for propane from the reaction below. with a delta H. So, okay. So there are literally only two versions of this problem. One where they want you to calculate delta H, and one where they want you to get the heat of formation of an individual piece. It should be super easy to tell which is which. Why? Because it's delta H here. If it's here, you got to get one of the individual ones. If it's not here, this is what you're solving for. It's literally that simple. And again, these are going to be magic word of formation. I don't care if it's enthalpy, heat, standard, they imply the standard, whatever. Of formation, reaction, look and see if you got a delta H. If you have it, you're looking for one of the pieces. If you don't have it, then you're solving for delta H. Okay, and every single time the first step is right here. The overall enthalpy change for the reaction is equal to the sum of the heat of formation of the products, including stoic, minus all of the reactants, including stoic. Again, this is really, do we get used to the symbols? Because the practice is not that hard. So here are my products, so let's start with that. So my overall reaction, which I have, I'm just going to leave delta H reaction here. So what are my products? Well, I have 3 CO2s, and I have 4 waters. And if you look, all you're really doing is just doing a little caret, delta HF. Little caret, delta HF. And you imagine on the reactant side, we're going to do the same thing. Little caret, delta HF, little caret, delta HF. And the only difference is the products are all positives and the reactants are all negatives. The book will typically do this with a parentheses and do a sum of all the reactants. That is correct. It might even be more formally correct, but I highly recommend you don't do it that way because it's very easy to lose a negative sign. I do it all the time if I don't factor right away. So just go ahead and just do products, positive, 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 and do the reactants, negative, 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 and don't worry about the parentheses. So in this case, we're going to have negative the heat of formation of propane, and minus 5 times the heat of formation of oxygen. So there's our symbols, and these are the numbers we need to look up. And again, I hope this wasn't that complicated. We literally just put little carets here and just did positives on this side and negatives. Remember, delta is products minus reactants, final minus initial. That's all we did. Okay, so now what do we do? Well, did they give us that number, or is that what I'm solving for? Nope, they gave it to me. It's clearly here. How about the heat of formation of carbon dioxide? Not in the problem. You might be wondering why it's over here in blue, or there's a CO2 with a number on it in blue, because I went to Bob, back of the book, looked it up. Actually, I looked in a table in a textbook. But regardless, wherever you find it, I don't care if you Google it, or use your book, or the index, or the appendix, or you flip through the chapter and find the table. However you get it, you can look up these values. So I found the heat of formation for CO2, or in a test, I would just give it to you in the problem, or on the back page of the test. Heat of formation of water, and I'll point this out. If you look up the heat of formation of water, you will see water solid, water liquid, water gas. In this particular problem, they say liquid. It's a standard state, which I just chopped off, which means 25 degrees Celsius, so water would be a liquid. So that's a liquid. If you want to be realistic and say it's in the middle of a fire and it would be a gas, you could also do that calculation. But do whatever they ask you to do. They put a liquid, I looked up the liquid. This is what they asked me to find, so I'm just going to put x there. And if this stoichiometry was 2 or 3, you'd have to have 2 or 3x here. You'd have to divide by that number at the end. I probably shouldn't have done one where the stoichiometry was 1, but just to point that out. The coefficient doesn't matter there. And then, how come I didn't give us the heat of formation of oxygen? Because if you look at the last thing in your notes from the last video, and I hope you are taking notes, you will see a little note there saying the heat of formation of all elements in their standard state is 0. Oxygen's standard state is O2 gas, so this value is 0. And from here, it's literally just some math. Whereas I like to say mathemagics. So 3 times 393.5 plus 4 times 285.8. I get negative 2,324 minus x. I think at this point, it'd be super easy to multiply everything by minus 1 and get rid of all those negative signs. 2220, 2324 plus x. Subtract 2324 from both sides. And I get x at minus 104 kilojoules. Or kilojoules per mole. Either way is fine for writing that. Does that make sense? Well, all my other heats of formation were negative. Dr. Werger said most of these things are either going to be a couple hundred or a couple thousand, so that seems reasonable. I feel good about this. I answered the question, and so should you. You should feel fantabulous about your work, and have a wonderful day.